Hi, we're back to session 2 of our EaganMatrix programming. And if you recall, in the first session, we created this brassy kind of sound by modulating one oscillator with another. However, this sound has a problem if my goal is to create a brass sound, because at the front, due to the low values of modulation, it's really more sine tone like, more organ like, and at the back it's too overmodulated, too buzzy. I don't like that. If we just kind of move our finger up, you can see the brass sound I'm looking for kind of starts about a quarter of the way, and then maybe to a little bit over half the way of the fingerboard. So I'm really looking to basically scale to the full height of the fingerboard, only the part of the sound that's brassy. I can't do that using just predefined formulas. I have to create some user-defined formulas to do it. And that's what this session will be on, how to create simple user formulas to replace the predefined ones that we looked at during the first session. But before we do that, I received some comments on the first video, especially regarding the use of the normal oscillator versus the integrated oscillator. And to be honest, I haven't played around with the integrated oscillator that much. And one of the good things about creating these videos is I learn a heck of a lot from the comments I get back. So I thought, let's start by looking at the normal oscillator and the integrated oscillator. Now, we don't really care about going into math behind digital summing and all the techniques that are used to create this stuff. I'm doing these videos more, I hope, for the uninitiated, technically inclined, because who wants to go through math formulas when your main goal is to make music? I'm not saying it's not important, it's just not the immediate goal of what I'm after here. So what I did was to create a simple preset that lets you play a normal oscillator on the bottom half of the fingerboard, increasing the full values from 0 to 1, so I can kind of hear all the different waveform possibilities of the normal oscillator on the bottom. And on the top half, I split it up so that I'm using an integrated oscillator. Now, the formulas that I used here, we'll be able to explain them pretty easily by the end of this session, because it's not really that difficult, though it looks kind of cool the way it's been programmed. The main thing we're after right now is just to hear the difference between what a normal oscillator and the integrated oscillator is. So let's just play around a little bit here. At the bottom, again, it's kind of sine tone like, increasing till I get a very buzzy kind of sound. You'll hear when I go between the split, you'll get a little pop. We're not interested in that, of course. So here's a normal oscillator. And here's the integrated. Again, starting pretty much of the sine tone. I don't hear much of a difference at the in the initial range. But at the top range, from like about 0.5 on, I can hear a distinct difference in the sound where the integrated oscillator has more of a much less of a buzzy kind of a sound. It's got a smoother, creamier sound, which I guess when you're just thinking intuitively about integrating something, you'd assume it's going to have a smoother kind of sound. And when you even look at the waveforms for the normal oscillator are a lot more jagged and edgy than the ones for the integrated oscillator. So I think this is a very good test for us to get a feel for when we might want to use one versus the other, though the ultimate proof of the pudding is going to be creating a patch and simply switching between them to see which one you like better, which is what we'll do when we go back to our preset. So let's go back to the patch that we created in the first session. And now we want to create some user defined formulas to scale just a part of that fingerboard that has the brassy sound so that the full fingerboard uses it. And what this will do is it'll expand the range of my brassiness so that I can get much finer gradations between the brass sound, which is important when you try and simulate a real instrument, because no matter what you do with the trumpet, you can play two notes, the same note. You're still going to have little differences in tone and inflection, because your lip pressure is never going to be exactly the same from note to note. Your lip vibration's never going to be exactly the same from note to note. And we can kind of simulate that on the fingerboard if the waveform is a little bit different no matter where I'm playing it, because I'll never play my fingerboard exactly in the center on each note. Your hand will be a little bit off. Okay, let's get to doing a user formula now. You'll notice on the right-hand side of the editor, we have the possibility to define a number of formulas. If you click one, at the bottom of the screen, you'll see your W, X, Y, and Z components come up, and each one of these components now can be set in various ways. I can do this so that I only change one of these components for a formula, or as you see, there's operators between these components, so I can have a formula that adds multiple of these things together to create different manipulations of the fingerboard. If I click the middle there, you'll see there's actually different sets of operations that I can use to add them and multiply them in different ways. And this is going to be very useful to create complexity later on. But right now we're after simplicity. So let's create a formula, A. Our Z formula, if you recall, is a squared function of pressure from 0 to 1. I can create a similar function myself by going to the Z component, and if you look, there's little red things all over the place that I can change. And if I just grab this circle and bring it up to max, this now will map my finger pressure from the very top of the fingerboard to the deepest point. So that's the function that's going to be applied going from 0 to 1, a squared function, which is a kind of a musical function. If I press in the middle here, you'll see I can get other shapes. If I want, I can get just a plain linear progression from lightest to heaviest touch. There's an S curve-like shape, Right? There's a square root kind of shape. And then there are a couple stepping functions we can use that basically are gating on at different levels to give you discrete changes in your pressure basically as you press. But we're really after this squared function, so we'll keep it there. Now what might you want to do with that? Perhaps you don't want to go all the way to max for a certain kind of a sound. You want to just go to maybe halfway or so, and so you can change your formula to do that. Now if you notice, there's little guide buttons around these components. That's an easy way for you to go to max, to 0, to min, and then there's some intermediary positions there, 0.5, minus 0.5. That's very helpful, especially the one that goes to min, because very often you'll play around with the formula and you want to just turn it off, and the way to turn anything off is to simply make your formula 0 out. All right, so we'll go and create pretty much the same thing as W, and what I can do then is where I have Z in the formula now, I can type my A's, and this will pretty much be doing what we had before. Okay. So there's a simple formula to put in there. I can do something similar on W, which basically, remember, is the gate that goes to 1 when your finger's pressed anywhere on the fingerboard, and 0 when you turn it off. So let's create another formula for ourselves, B, and there's our W component. If I want, I can expand this out and go to 1. All right. If, again, it's hard for you to get exactly to 1, just press your guide button. That will get you to 1. 1's a very important number when you create formulas. It's used all the time. So now W basically does the same thing we had before, goes directly gating to 1. But perhaps gating right to that full value is not what we want. Maybe we want to have a gate that gates a little bit less, maybe to 0.9. So I can change it to do that, and instead of where W is now, I can put my B, and this will sound pretty much the same. Maybe it won't have quite the same kind of an attack. You could do something similar. I could pull that up to be a little greater than 1 if I wanted to have maybe have a greater attack on the note. But it's really this Y component that we're most concerned with in changing our formula here, because Y is what we need to change to be able to scale the sound the way we want. I want to get rid of that sininess at the bottom, and I want to get rid of that modulation at top. So if we start around a quarter of the way up, let's say we want to create another formula, C. Now here I can set the sides of Y. And the way this works is the left-hand side of this Y component is the bottom of your fingerboard. The right-hand side is the top. So what I can do here is I'll start at the bottom of my Y. Say I'll start at I don't know, let's start at 23, that's fine. And let me go up to something like 60. Okay. So now when I play on the fingerboard, the very bottom will start at 23, top will go to 60. You'll also notice this defaults to a little step ladder at the beginning and the end. And what that's useful for is I would like to make sure that the full width of my finger is playing the value that I want at the bottom. I could, if I wanted to, with these little red dots, make it totally linear, but let's just keep it with that little stair step for now. Okay. If you notice, I can still have in the different kinds of functions, but for right now, linear is what I'm after. because I want a steady increase in that value. Very important function up top. This one maybe not so much for now. It allows this function you define on the different components to be either a continuous or be applied initially, and a couple other types of functions that are less used. You can read about in the manual. We'll cover that later maybe. But this is very important. The second item up top is your scaling factor. A lot of times you may not want to go from 0.2 to 0.6. Maybe I want to go 10 times that, or even 100 times that. Or sometimes for certain functions, especially the biquad banks, you want small values, so I can scale things very small if I like. Extremely important function for you to control your components. But for now, we want to go from about a quarter of the way up to 0.6, say. And since we have this set to formula C, let's replace the y's that we have now with c's. Okay. Now, hopefully, when I play the fingerboard, I'm going to get a brassy sound all the way through. Yeah, now at the bottom, it's kind of brassy to begin with. And up top, it still sounds a little overmodulated. So perhaps we want to bring this 0.6 down a bit. Maybe we'll bring that down to 0.5. Okay, now a little better at the top now. So my full range through the fingerboard. Not much better. If anything, maybe I can reduce that top even a little more, but we'll leave that for now. All right. Another thing that we can see here is that at the bottom, we're, a little more mellow, and at the top, a little more brassy. But let's play around with our oscillators, because perhaps we're just using the default ones now. Perhaps going to integrated might improve the sound or not. So let's see what happens if I change to integrated oscillators. Hey, you know what? Let's go back. And that's a little more buzzy. I'm convinced. I think the integrated oscillator, which gives us that smoother sound, is better for us here. A nice low brass sound there. And now, sounds kind of like a flugelhorn at the bottom. Yeah, that's kind of nice. All right. But perhaps we can do something else. Right now, I'm using the same Y component to control both the S and the modulation amount. Maybe we want to make the modulation amount a little less, or do it in such a way that I can have independence on the amount of modulation versus the waveform change. So let's create another formula for ourselves, and maybe for this one with Y, we'll go from maybe 0.1 to I don't know, 0.4 instead of what we did before. And on C now, let me use D. I get a little mellower tone at the bottom. All right, I could twiddle a bit more with that and try and find ranges that are better. perhaps, but I like it the way it is. So let's save that to a path. Let's call that brass 1. Okay, now what we want to do is go back to our split oscillator example, and we know enough now to explain how this cool little patch was created. If you recall, this is a patch that lets us play on the bottom half of the fingerboard the regular oscillator, the normal one, and the integrated oscillator on the top. So let's see how this was done. Obviously, there's two oscillators defined here, the normal one and the integrated one, and they're both channeled out to the outputs, though only one is going to play at any given time. They're both tracking X on the fingerboard to the pitch that I expect, right? But now we have some user-defined formulas, very simple ones, that do the trick for us. So let's take a look at the first oscillator. What I'm doing is I'm multiplying the frequency times a y function. And what this is saying to me is as y goes left to right, I'm going to set y to a value of 1 right to the midpoint, and then I'm going to set it to 0. So what's that going to do? It's going to multiply the frequency that's being played by 1, which is the frequency that will play until the midpoint, and then that frequency will be multiplied by 0 from the midpoint to the top, effectively stopping any sound from coming out of that oscillator. Hey, that's pretty simple. Now that gets combined with this function because I want y from the bottom to the midpoint to run the full range of S values, waveform values, from 0 to 1. Now, unfortunately, I can't start y at the bottom left at 0. It defaults down there to -1, which is fine, because now it lets me show you how to use another formula in conjunction with one I have to create a compound formula. So now let's see what's going on here. This is going to go from -1 to 0, and then go from remain 0 from that point on. Though I don't really care what it does after midpoint, because we've already seen no frequency is going to come out after that. So what I'll do is, because I really want this to go from 0 to 1, I can define now a fixed W formula. So as long as my finger is pressed on the fingerboard, this is going to basically apply a constant value of 1. When added to my -1, starts me at 0, and I'll get exactly the function I want from the bottom half to the mid half, going now 0 to 1. Easy. The second half, and how do I, let's get rid of the second half, by the way. All right, well, we won't route that to output, and let's now play in the fingerboard. And you can see from the top up, sound disappears, comes back on as I play the bottom half of the fingerboard. Okay, let's turn back on the second oscillator. Now the second oscillator does kind of the inverse. What I'll do here is, for the first half of the fingerboard, I'll have y basically set to 0. So nothing will come out on the first half, and then from the second half of the fingerboard, it'll be set to a constant of 1. So basically, whatever my frequency is at that point will be played. Great. Now, I'll do the opposite on the y. And in this case, it works out nicely that I can go from 0 to 1 from the second half of my y function easily, because I can start at 0 and move to the midpoint there, and then increase linearly to 1. Hey, that's all I need to do. And so the second oscillator then plays from midpoint to top. Pretty simple, and I think you should be able to easily understand that based on the simple functions that user functions we've created today. All right, that's enough to digest. We haven't really talked about the complexity of changing X, which can do some kind of nice things. You can create functions that say will only play in a certain area of the fingerboard. You can set quantization on this so that you can get a stepping function between notes like you would on a keyboard, for example. We'll talk about that later. So I think the next time what we'll do is we'll take a look at creating barrels and how to control things dynamically through the setting of these controls, which you can either set by your mouse, or if I have a device with knobs on it that allows me to map it to these controls, I can use that. Or I can even set a pedal up and control these things with that. And we'll take a look at how to do all that next time. Okay, that's it for today.